Hi, it's Mrs. Cat, and I'm here to talk about Lewis structures. And so far, when we've been representing compounds, we have been using particle diagrams. And while they have served us very well, and we will continue to use them throughout the rest of the year, they really don't do a very good job for us at representing the presence of electrons and chemical bonds in structures. So Lewis structures are named after Gilbert Lewis, who in 1906 came up with this model for using lines to represent shared pairs of electrons and dots for unpaired or unbonded electrons. Okay, this is what we're going to do to represent our chemical structures on paper. We've already got a little preview of this through the covalent bonding and Lewis structures activity that you've done, comparing valence particle diagrams to Lewis dot diagrams to a Lewis structure. So all of this is central to the idea that by sharing electrons, we want to achieve a full valence shell, and this is how our atoms are going to combine. So just a reminder that this is for most atoms, a full valence shell is 8 valence electrons. Okay. Some exceptions would be hydrogen and helium are full at 2 valence electrons. Okay, and that's because they're small. They only utilize the first energy level of electrons, so that's going to only be able to hold 2. Okay, so we're just going to dive right in and look at some examples as to how to draw Lewis structures. When we draw Lewis structures, okay, the first thing we want to do is to find the total number of valence electrons. Okay, we're going to use all of those together to come up with our structure. Okay, then we want to determine the central atom. Okay, or our center atom. We're going to look at this a couple of different ways. Okay, sometimes it's really easy to see. Maybe there's only one atom of that element present, and so it makes sense that that would be the center atom. The other thing that you might want to look at is that you're going to look for the lower electronegativity value. Okay, those are some good clues as to which atom is going to go in the center. Okay, and then you will want to look at placing your electrons. So place electrons in bonds. Remember, these are shared pairs. And lone pairs. Okay, these are non-bonded to achieve full octets. Now, full octet, that's really not the best way to say this. We want to say to achieve a full valence shell for all atoms. Now, this is often referred to as the octet rule, since most atoms, again, are going to have a full shell with 8 valence electrons. But because we have those exceptions of hydrogen and helium and some other situations where you may not have exactly 8, we're just going to say have a full valence shell. So let's get into our examples. Let's start with methane and ammonia and water. Actually, we'll just go ahead and look at these 3 all at once, because these are 3 covalent compounds that go by common names. These 3 are you're obviously going to want to know, because these are the way, this is the way that we're going to name them. You know, water, don't worry about that. We're not going to call it dihydrogen monoxide. But methane is CH4. Methane is natural gas. And whenever you see methane, you're going to write CH4 as your formula and vice versa. The other and last one that we're going to use a common name for is ammonia, and that is NH3. Okay, so now let's get to their Lewis structures. Methane, CH4. So we're going to start by adding up our total number of valence electrons. Looking at the periodic table, we can see that we have 4 valence electrons for carbon, and each hydrogen has a total of 1 valence electron, and that's going to give me a total of 8 valence electrons to use. Okay, can't use any more, can't use any less, I have to use all 8. Okay, now based on what I have in my formula, there's only 1 carbon, it's going to need to go in the center or be our central atom. Okay, I'm going to go ahead and place my hydrogens all around because I know that the carbon's going to be in the center. Okay, and then we can place our bonds in between these. Okay, each bond that we place, we're going to represent with a line for that shared pair of electrons. Okay. And it counts as 2, right? So at this point, if we count up our total electrons that we've used, 2, 4, 6, 8, right? We really want to think about this as being a pair of electrons, 1 coming from each bond. Okay, so we want to check to make sure that we've done what we need to, which is use up all of our valence electrons and make sure that every atom has a full valence shell of electrons surrounding it now that we've shared those electrons. So let's take a look at carbon. Okay, we just counted those up already, but let's focus on it here. Okay, there's 4 bonds around carbon, giving it 8 valence electrons. So carbon is good for its valence. Okay, each of the hydrogens, each of our hydrogens has 1 pair, that carbon back in there, 1 pair of electrons surrounding it. Okay, with a bond, that's 2 electrons, which is going to give hydrogen a full valence shell. So we've got a good, complete Lewis structure. Okay, so we're going to wind up with carbon in the center, 4 hydrogens around, 4 bonds all together. Okay, another example here, let's look at ammonia. Nitrogen has 5 valence electrons, 3 hydrogens at 1 apiece, give me a total of 8 valence electrons to use again. Okay, again, it's pretty clear here that we're going to have the nitrogen in the center because there's only 1 of them. I'm going to put my 3 hydrogens around, okay? And then I can place a bond between each of them, okay? Each bond represents 2 electrons, 1 coming from each of our atoms. So those are shared. I've used 6 electrons so far. I have 2 more that I have to use, so I have to figure out where to place them. I don't have any more atoms to bond, so I want to go ahead and check and see what's going on with the valence electrons to determine where these need to be placed. So let's take a look at the hydrogen first. All 3 hydrogens are the same. 1 bond to the nitrogen, that represents 2 electrons, so that's going to have a full valence shell. Hydrogen is good. Okay. If I look at nitrogen, we have those 3 single bonds between the hydrogens, that's 6 electrons. Nitrogen will have a full valence shell with 8 total electrons. So what we want to do to give a full valence shell to nitrogen is to place those remaining 2 electrons on the nitrogen as a non-bonding pair, and we show that again with dots. Okay, we call that a lone pair of electrons. It's a non-bonding pair. So now we can see that nitrogen has all 8 electrons it needs to have a full valence shell. We've used all 8 of our electrons that are available to us. That is our complete Lewis structure for ammonia. Water, H2O. Again, hydrogens, whoops, we're going to have 2 of them, each with 1 valence electron. If I locate oxygen, it's in period 16, or group 16. There aren't 16 periods on a table. Group 16, all of those elements have 6 valence electrons. So guess what? 8 valence electrons to use this time as well. Okay. Oxygen goes in the center. There's only 1 of them. I'm going to go ahead and bond those hydrogens using up 4 of my electrons. Okay, I hope by now we're starting to notice that hydrogen is good to go after one bond. It can't do anything else to form one bond. Oxygen right now only has 4 electrons surrounding it, so those other 2 pairs of electrons are going to have to be placed on the oxygen as those lone pairs. That takes care of all 8 of my electrons I have to use. That puts a full valence shell on all of my atoms. This is water's Lewis structure. Taking a look at the last one of these first 4, we have hydrofluoric acid, which is HF. Okay, 1 electron in the valence shell of hydrogen. Fluorine has 7 valence electrons for a total of 8. Once again, this one's going to be pretty straightforward. Obviously, 2 atoms, there's only going to be 1 possible bond. Okay, hydrogen has its 1 bond, it's set, but we've got 6 electrons that we still need to place. They have to go on fluorine because fluorine does not yet have a full valence shell of electrons surrounding it. This is going to give fluorine 6 non-bonding electrons, 2 bonding electrons, fills its valence shell. We've got all 8 of our electrons used. Okay. So those are all pretty simple and straightforward. Let's look at a few more, okay? We are going to have some compounds that contain multiple bonds in them in order to give them a full valence shell of electrons. Now, you shouldn't go seeking these out and assuming that these are going to happen from the get-go, but what we do want to make sure that we do is use up all of our electrons, give everything a full valence shell. If you can't do that by simply placing bonds and lone pairs, we're going to have to do some rearranging to get to those qualifications for a correct Lewis structure. So let's look at 3 examples where that's going to be the case. We've got chlorine, which is diatomic. Looks like I got something funky going on with my connection here. Let's see if I can reboot this. Okay, that's better. So chlorine, 2 of them, 7 valence electrons apiece because it's in group 17. This is going to give me 14 valence electrons to use. Okay, each of the chlorines is going to be bound to one another with 1 bond. Okay, that's 2 electrons so far. I don't have any other bonds that I'm going to place right now. I'm going to go ahead and put our lone pairs or the non-bonding pairs around the chlorines until we get a full valence shell for each. So I've got 2 electrons I've used so far, 4, 6, 8, 10, 12, 14. That uses up all of my electrons. Now we want to check and make sure that we've got 8 electrons surrounding each chlorine. So these chlorines are identical. We've got 1 bond, that's 2. Okay, and then 2, 4, 6 more gives me 8 valence electrons around the chlorine. So that diatomic chlorine is good to go as it is. Okay, oxygen is also diatomic, but oxygen has 6 valence electrons per atom. So here we have 12 valence electrons to use, so 2 fewer. So we're going to start off the same way. We're going to bond those 2 oxygens together and start placing valence electrons that remain as lone pairs around these atoms. So we've got 2 from the bond. There's 4, 6, 8, 10, 12. I can't add any more electrons because that's all that I have available to me. So now what we have to do is check and see what's going on. So let's check this oxygen that's on the left. Okay, I see 1 bond and 3 lone pairs. That's a total of 8 electrons. So that oxygen's set. Okay. If I look at the oxygen on the right, this only has 1 bond and 2 lone pairs around it, which does not give it a full valence shell of electrons. When we run into a situation like this, we're going to have to rearrange the electrons and share more so that we can get all atoms to reach that full valence shell. What we want to do here is take one of the lone pairs from the oxygen on the left and change it into a shared pair. So it doesn't really matter. I'm just going to erase one of these. Whoops, I need to keep the oxygen though. Okay, I'm going to take away one of those lone pairs. And now I'm going to place another shared pair in between the two oxygens. This is going to create a double bond. Now, if I check these oxygens, they each have 2 bonds and 2 lone pairs, okay, which is 8 valence electrons surrounding. Now, each of those oxygens is going to be set, okay? So again, if you've placed all your electrons and you can't reach a full valence shell for all of your atoms, then we want to rearrange some lone pairs and place them as multiple bonds. Let's do another example of that, looking at carbon dioxide. So carbon, whoops, pull this back up here. Carbon has 4 valence electrons because it's in group 14, 2 oxygens, 6 each. Okay, I've got 16 valence electrons to use in this structure. Okay, carbon's going to go in the center. There's only one of them. It also has a lower electronegativity compared to oxygen. So that's going to use up 4 of my 16 electrons. Okay, I'm going to start placing the rest of my valence electrons around, starting on the outside atoms. So that's going to be my oxygens. So 4 already. There's 6, 8, 10, 12, 14, 16. Okay, great. Oxygens, let's check those first. They look exactly the same. There's 1 bond and 3 lone pairs. That's 8 electrons surrounding each oxygen. Fantastic. That's what we want to get it to. Carbon, on the other hand, only has 2 bonds. That's 4 electrons. We want to get carbon to a place where it has a total of 8, so it needs 2 more pairs of electrons to be surrounding it. In order to do that, we're going to have to move lone pairs. So I'm going to take 1 lone pair from the oxygen on the right, keep erasing my oxygens, and shift it to be a shared pair, giving us a double bond. We do the same thing on the other side. Whoops. Take my lone pair of electrons, change it into a shared pair, making another double bond. Okay. Now, if we check oxygen, 2 bonds, 2 lone pairs, that's a total of 8 on both ends. The oxygens are set at a full valence shell. Carbon now has 4 pairs of electrons, 2 double bonds, okay, or 4 bonds altogether, 8 valence electrons in its Lewis structure. Okay. So that's our basics of Lewis structures. I'm going to do a few more examples in a separate video of some exceptions and walk you through some more. But this is a good place for you to get started and to start trying out your Lewis structures.